Now, we're going to talk about something called dimensional analysis. And dimensional analysis is a very important way of using units and converting from one unit to another unit. And we're going to do a couple problems here in order to discuss this. Dimensional analysis is just a fancy word for how we change from one unit to another. And you can see here is a problem. It says a light year is the distance that light can travel in 1 year expressed in miles. If the distance, excuse me, if the speed of light is 300 million meters per second, how far is 1 light year in miles? Okay, so how far can light travel in 1 year in miles? And so we're going to use dimensional analysis to convert this, and I've given you the one number that you have to know in order to do this, that we can travel 300 million, my handwriting's not so good, meters in a second. Now, we can either first convert seconds to years, or conversely, we can convert meters to miles first, and then seconds to years. So let's start with the meters to miles. Remember, there were 1,609.334 meters in 1 mile. Now, the reason I wrote it this way is you can then cancel these 2 meters out. And what I've done is convert this meters to miles per second. Okay? And then after that, what we have to do is convert seconds to years. And so we have 3,600 seconds. And that's 60 seconds in a minute and 60 minutes in an hour. So that's 1 hour. And then there's 24 hours in 1 day. And 365.25 days in 1 year. 8 times 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So a light year is 5.88 times 10 to the 12th miles. That's the distance light travels in 1 year. And this is called dimensional analysis, where and the dimensional analysis part is where we take all these various dimensions or units and we can cancel out each one until we're left with miles on the top and years on the bottom. And so that's how far light travels in 1 year. Now, for just interest's sake, what was the other problem here? Let me move this over for just a second. Let's say the average person weighs 160 pounds. What is that person's weight in kilograms? Okay. And the conversion factor I gave you is 0.4536. So 160 pounds. And it's 0.4536 kilograms in 1 pound. So how do we do this? Well, now we can get rid of the pounds here. So now we know 160 pounds. If we multiply these two numbers, that we'll know how many kilograms that is. Well, 1 kilogram is 1,000 grams. Kilogram means 1,000 grams. And 1 gram is 1,000 milligrams. This one, we get 7.26 times 10, 3, 4, 5, 6, 7 to the 7 milligrams. So we've converted 160 pounds to 7.26 times 10 to the 7th milligrams. So that's converting units using dimensional analysis. Move on with some new definitions. What we just worked with is known as a conversion factor. A conversion factor is a ratio that relates one unit magnitude to a similar, and that's important that it's a similar unit magnitude. For example, in this case, you see that we're converting one length, the meter, into another length, the centimeter. And this conversion tells you how many centimeters are in a meter, and you can invert this in such a way as to show how many meters are in a centimeter. Now, the second thing I told you we were going to review in general was the idea of accuracy. Accuracy and precision are two ideas that we have to be distinguished, because we're going to be talking about significant figures here in just a minute, and significant figures are a measure of precision and not accuracy. Accuracy is the degree to which a measured value agrees with the truth. So, for example, in God's mind, you have a certain weight, say 160 pounds, and that's the real true value for that weight or mass. Accuracy is the degree to which your scale, your measuring device, agrees with that true value. On the other hand, precision is the degree to which repeated measurements agree with each other. Notice it doesn't have anything to do with the true value. So a measuring device can be extremely precise and inaccurate at the same time, or can be accurate but imprecise. And so it's important to understand the difference between these two, because when we talk about significant figures, we're talking about something that expresses precision, not that expresses accuracy. And it's very important to understand that you need to make sure you express your results with the proper degree of precision based on the precision of the measurements, and understanding the definition of precision when I use it there. So here's an example of a precise measurement that's inaccurate. You see here that the dots are concentrated very close to each other. So repeated measurements or repeated actions that are very close to each other. That is highly precise, or has a high precision. However, they're not very close to the bullseye, and so the accuracy is low. Conversely, if you're trying to hit a bullseye, in this case they talk about a GPS system trying to locate a restaurant, in the center would be the bullseye. The black dots represent each indication of where the restaurant is, or each shot at the bullseye. You notice the dots are very far from each other, but they're reasonably close to the bullseye. So they have low precision but fairly high accuracy. Now, significant figures are a measure of precision and not accuracy. So as we go through the rules for significant figures, we have to remember that we are trying to retain the precision of the measurements in the answers that we give. The key thing to remember is the precision of your answer cannot be greater than the least precise measurement. And so the number of significant figures of an answer cannot be greater than the number of significant figures in the least precise measurement, or the measurement that has the lowest number of significant figures. So that's why we're going through all these rules, is so as you do problems, you understand how to express the answer in the proper precision. First of all, it's very simple. Any non-zero number is significant. Now, where things become exciting is when we talk about zeros. If you put a zero between two non-zero numbers, it's significant. So, for example, in these cases, the 4 and the 5 are significant because they're non-zero numbers. The 0 in between is significant. The 6 and the 2 in the 6002 here is significant. Therefore, the 2 zeros in between are also significant. The next example has both significant and non-significant zeros in it. The 3 zeros between 1 and 3 are significant because they are between 1 and 3. But the other zeros here are not. And so this number has 5 significant figures. Zeros at the end of the number, extremely important, with a decimal, is significant. At the end of a number with a decimal are significant. And so here we have 3 zeros at the end of this 14. There's a decimal here, and so those 3 zeros are all significant. The next one shows 2 significant zeros and 1 non-significant zero. The first 0 is not at the end, and so it's still not significant. But the other 2 are at the end, and there is a decimal present, and so they are significant. Zeros at the end of a number without a decimal are not significant. And these examples, the first one, there are 3 zeros, but there's no decimal, and so you have 1 significant figure here, 2 for the next one, and 2 for the next one. Now, if you wanted to show that any of these zeros were significant, all you would have to do is put a decimal at the end where the commas are in the first 2. And if you put a decimal there, then suddenly those zeros become significant. Now, another way to think about this as we go to the problems is if the 0 is functioning only as a placeholder, then it is not significant. However, if it is functioning to show that the measuring device is saying 0 instead of some other number, then it is significant. So if we go back, if you look at the bottom examples, those zeros are only placeholders. In the first case, to show that the 4 is in the thousandth place, it's just those 3 zeros are just a placeholder, and so they're not significant. The same is true for the others. But if you move up to the next example, 14.000, those zeros are to show that in the 10th place we have a 0 instead of a 1 or a 2. In the 100th place we have a 0 instead of a 1 or a 2. And in the 1000th place we actually know that that's supposed to be a 0 instead of a 1 or 2. If the device did not measure to that degree, you would just leave that blank and not put anything there. So let's look at our problems. For each of the following numbers, give the number of significant figures. The answer here is 3. The first 0 is just a placeholder. It's not at the end of a number, it's at the beginning, and so the fact that there's a decimal doesn't matter. So that first 0 is not significant, But the second one, which is between two non-zero numbers, is significant. So 3 significant figures here. This is very similar to what I showed you as an example. These 2 zeros are at the end of a number without a decimal, so they're not significant. These 2 zeros are placeholders, so they're not significant. So there's 2 significant figures in this number. The answer here is 5. The 0 is between 2 non-zero numbers, and so it is significant. So there are 5 significant figures in this number. Okay, we have 4 zeros here, but there are only 3 significant figures. The 2 non-zero numbers obviously are significant. We have a decimal, so the 0 at the end is also significant, but the other 3 are not at the end, and so they're not significant. They are also placeholders, so they're not significant.